Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I am Dr. Sababau from the Physics section, Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This is course JRF 318 Quantum Mechanics. This is the chapter 1, Introduction to Quantum Physics. You are in segment unit 1.1. This is basically preface to quantum mechanics. After this lesson, we hope that you can understand and able to explain the perspective of quantum mechanics with respect to the concepts of classical physics. I think you are familiar with classical physics. For example, like in mechanics, in optics, in waves and vibration, all those are in classical physics. But now we are going into quantum mechanics. Before we go into the topics of quantum mechanics, we might as well recall the start of the quantum physics. Okay, quantum mechanics basically the mathematical formalism of quantum physics based on quantum physics. As a preface, quantum mechanics is the gateway to modern physics. I think you have also studied modern physics in the lower level. Stern phenomena you have come across in the course of modern physics, basically based on quantum physics. So quantum mechanics is a gateway to understanding the modern physics. Okay. Classical mechanics is nearly 400 years. I mean, from the time of Newton, we have the Newtonian mechanics and so on and so forth. Classical electromagnetism is more than 100 years old. Electromagnetism, you study electrostatic and so on and so forth. Whilst the exotic discoveries and theories for subatomic particles and cosmology is in the past few decades only. That means just less than 100 years. Okay, this is why due to quantum mechanics. Without quantum mechanics, these decades in these few past decades basically will not be able to present us with understandings of subatomic particle. When we say subatomic particles in an atom basically, just like orbital electrons, and of course the nucleus, which is containing protons, neutrons, and other elementary particles. Atomic nuclear particle and condensed matter physics, atomic physics, nuclear physics, particle physics, condensed matter physics are all based on quantum mechanics. Basically, without quantum mechanics, people will not understand what is going on in these atoms, nucleus, and also in condensed matter physics, basically in solids and so on and so forth, solid state physics. To a large extent, the story of 20th century physics is the story of quantum mechanics. Basically, whatever we have, the understanding of whatever scientific properties, characters in atomic, nuclear physics, and so on and so forth, is basically the story of quantum mechanics. So that's why quantum mechanics is very crucial for physicists. Quantum mechanics requires a radical shift in the way we view reality. Of course, it causes trouble to some of us. It's quite troublesome to some of us because most of it, the concepts and the principle is sometimes is not based on whatever the conception we have in our mind, and of course the formalism and analysis are based on mathematics and higher level mathematics. Okay, so quantum mechanics uses several areas of mathematics. Basically, mathematics is the language for physicists that are not frequently encountered in classical mechanics or electromagnetism. In classical mechanics and electromagnetism, usually we use simple mathematics, but in quantum mechanics, we need to have a good understanding, good grasp of complex numbers, linear algebra, calculus, and so on and so forth. The prerequisite for you before you sit for this course is classical mechanics. I think you have done this, electricity, magnetism, and of course modern physics. As an introduction, classical physics basically when we say classical physics, usually classical mechanics based on Newtonian mechanics. Electricity, magnetism based on all those formulas and equation in electricity and magnetism, including electromagnetism itself, and thermodynamics. Okay, while modern physics, which grew out of quantum mechanics, when is found in atomic physics, nuclear physics, particle physics, condensed matter physics. Okay, let us recall what were the propositions of classical physics. The first one, the physical universe is deterministic. For example, when we say that I'm sitting on a chair, then it is deterministic. That means your location in terms of 3D, X, Y, Z axis is specific. That means you can determine your location according to X, Y, Z axis. Okay? Okay. Then light consists of waves, while matter is composed of particles. Those were the proposition of in classical physics. When we study refraction and reflection of light wave, for example, we use Huygens wave France principle to determine how the light waves were reflected or refracted, or in terms of diffraction, how it is diffracted. We use in schools and in early days, we use a compass and a pencil to draw the wavefront and so on and so forth. And those were valid. Basically, we can understand the process of reflection and refraction. While matter is composed of particles, we know that matter, when we say matter, it is made up of solid, liquid, or gas, whatever it is, should be composed of particles. So there is a distinct separation between light as wave and matter consists of particles. Okay. The third one, physical quantities such as energy, angular momentum can be treated as continuous variable. So energy, for example, when we go cycling, for example, when we start cycling and so on and so forth, we know that our energy in our body decreases continuously. So energy and angular momentum can be treated as continuous variables. That means the change in energy or angular momentum changes in continuously. That means the amount, whether it increases or decreases continuously. Number 4, there exists an objective physical reality independent of any observer. That means when we observe an event, for example, so it is independent of the observer. For example, if you go in the forest, we saw a leaf falling. Okay, so whether we are observing it or not, the leaf will go on falling. Whether, for example, I'm staying in my room, of course, according to our intuition or our perception, whatever leaves in the forest will keep on falling, whether I look at it or not. Okay, that's the normal or intuition. That means we think that the world around us will go on as it is, whether I'm looking at it or not. However, when the concept of quantum mechanics was introduced, so those things, I mean, whatever we have already, the concepts in our mind, basically were or are jeopardized. That means quantum mechanics say that they are not completely accurate. And that's the conclusion. Quantum mechanics says that they are not completely accurate, whatever four propositions in classical physics. The first one, the physical universe is not deterministic. That means we cannot determine exactly the position or momentum of anything. So what they have to do, basically, we assign probabilities. That's why probability is important in physics, and of course is one of the topic in mathematics. Basically, the probabilities, the maximum probability, we cannot say exactly for sure something is like this and like that, except that most probably, that depends on probability. It never predict the exact result with certainty. Okay. Never. Usually in the schools, some people say that science is an exact knowledge. That means we can determine exactly. But when we were in undergraduate or in upper secondary school, we start to understand that any measurement in physics there is an error, plus minus. So if your measurement has no error, so it is wrong. Now in universities, you learn that there is never an exact results. Okay, with certainty, of course, there is a probability. That means apart from plus and minus, you have to take into account the probabilities of an event occurring or not. Okay. The second one, both light and matter exhibit particles and wave properties. Just now, in the old physics, you say that light is a form of wave and matter uh, they consist of particles. But now, both light and matter exhibit particle and wave properties. Later, we'll discuss this. Okay, light, or even though it is massless, it also exhibit particle-like properties, such as later we'll discuss in photoelectric effect, Compton scattering, and so on and so forth. While matter, that means matter consists of particles which have mass. We are matter. Myself and our world around us are all made up of matters. They have wave properties. So how come people like us have also wave properties? That will be discussed in the future segments. The third one, some physical quantities are quantized. Quantized means they have discrete values. It is not continuous. That means Stern energy, for example, has Stern values as in between the values. You cannot have that type of energies, for example. Okay, that means some physical quantities are quantized. That means it can only occur or available at Stern values, and in other values it cannot be. Okay, tak sah lah. The fourth one, it appears that the observer always affect the experiment. Okay, that means when we want to observe something, we need to have something, because our eye, for example, if we are looking at something, we need something to be available so that we can see the object. For example, if I hold a pencil in front of me, in order to see the pencil, I need to have light. Okay, if it is dark, I cannot see the pencil. Okay, so when you have light, that means light photons or light wave is bombarding the pencil. Okay, so when we want to observe the pencil, we have to some sort of like put something affecting the pencil, such as light. But of course, we cannot see that by shining a light on a pencil, the pencil will be pushed away or something like that. But later in future segments, we will see that for microscopic particles or atomic and subatomic particles, if you use light or any other form of photons such as laser or particles, then you are affecting the object you want to see or you want to observe, such as you want to observe a particle, a subatomic particle. The particle will absorb some of the energy, and of course it moves away or whatever happened to it, may be excited on so on and so forth. So in quantum mechanics, we say or propose that the observer always affect the experiment. Why would anyone believe in those ideas? Okay, the classical physics is well established. It's a few hundred years established, firmly established, should I say. But how can we have to believe in quantum mechanic ideas? Because it works. Okay, in order to explain some of the subatomic phenomena, quantum mechanic ideas work, while classical physics fails to explain some of the phenomena. For example, if you want to explain photoelectric effect phenomena, you cannot use classical physics. Basically, it fails to explain why photoelectric effect occurs, or in case of Compton scattering, or even as simple as black body radiation. Later, we'll discuss in the future segment. Quantum mechanics allows us to explain physical phenomena primarily at very small length scale. That means subatomic or atomic particles. That means at small dimension, for which classical physics simply offer no explanation. That's why we have to accept quantum physics or quantum mechanics. Okay, especially for microscopic physics or atomic or subatomic particles. Quantum theory ultimately prevailed because it agreed with experiment. When physicists propose stern hypotheses or proposals concerning a few physical phenomena, then experimental physicists usually try to prove or disprove that theory or proposal or hypothesis by doing experiment. And we found like that uh, the experiment agreed with what was proposed by quantum mechanics. In each of the experiment below, for example, physicists had developed a classical theory which failed to account correctly the experimental result. For example, black body radiation. This phenomena, black body radiation, photoelectric effect, Compton effect, were already known quite long ago, and scientists have tried to explain why the phenomena occurs by using classical theory, but all those theory or the classical theory fail to account correctly. Okay, quantum mechanics has proven highly successful in analyzing the behavior of atoms, explaining many atomic phenomena where classical theory fails. Okay, when classical theory fails, when we use quantum mechanics, especially for microscopic situation, then basically quantum mechanics is or were highly successful. Okay, quantum mechanics attempt to combine the wave-particle duality. Basically, this is the basis for uh, quantum mechanics. You have studied this in modern physics, where a particle have wave-like properties, and wave have particle-like properties. So basically, quantum mechanics combine the wave-particle duality into a single consistent description. Later we'll discuss Schrodinger equation. Basically, in the Schrodinger equation, it takes into account both the wave properties and the particle properties of whatever you have, whether it is light or photon or particles. The basis for our present understanding of microscopic and submicroscopic phenomena is quantum mechanics, of course. So the question is, does that mean quantum mechanics defeated classical physics? That means classical physics is wrong and quantum mechanics is right. Actually, no. When quantum mechanics is applied to microscopic phenomena, okay, it reproduces the result of classical physics. That means what we can say that classical physics is a special case, while quantum mechanics can explain whatever case you have. Okay, for example, like quantum mechanics, when you apply to microscopic phenomena, for example, like a person walking, whether a person is matter, whether that person produce wave, and quantum mechanics can prove that that person actually produce wave, which is called matter wave, which we'll discuss in the future segments of this e-kuliah. Okay, so actually we can reproduce the result of classical physics. That means from quantum mechanics you can get the result of classical physics, but the other way around might not be possible in certain cases. Okay, you cannot use classical physics to prove and then you to get quantum mechanics formulation, but from quantum mechanics formulation you can reproduce the results of classical physics. So quantum mechanics is a consistent theory. That means it can be applied to any situation, whether macroscopic or macroscopic, whether to a small particle such as an electron or to a big matter such as human being. However, no need to abandon the laws and principle of classical physics. The two theories complement each other. So basically, for macroscopic world, Newtonian mechanics is still applicable. People use this principle for engineering purposes. You cannot say that you cannot use Newtonian mechanics. They are still applicable for microscopic world, but quantum mechanics basically can be in microscopic or microscopic worlds. As a conclusion, classical physics is still valid for macroscopic phenomena, but fails to explain microscopic phenomena. Quantum mechanics is based on the concept of wave-particle duality, And commonly, classical physics phenomena are the special cases of quantum physics. That we'll see later, for example, when we discuss black body radiation, classical physics used by Rayleigh engine try to explain the distribution of uh, of uh, black body radiation. It failed, but it failed at certain frequency. But for quantum physics or quantum mechanics, it can explain the whole of the spectrum of black body radiation. And when we try to use the frequency at where the classical physics is correct, and again we get the formula of religion from the quantum mechanics formalism. This is just an introduction. The detail will be in, we'll discuss them in our future segment, inshallah. Thank you very much for your attention.